Hey folks, welcome back. This is Joel, and in this video we will talk about NAT64. Alright, so we'll talk a little bit about the technology and then we'll go to the lab. Alright, cool. So that being said, let me pull up my whiteboard. So we'll be actually doing this lab on CML, right? Probably this is the first time I'm using CML on the channel, but it's a pretty similar tool, just like our GNS3 and EVNG, right? Okay, that being said, so what do we have, right? Before talking about NAT64, I just want to kind of explain to you the problem at hand, right? What do we have here? On the left hand side, we have a very typical enterprise network, right? So you've got an access switch, you've got a distribution, there are a couple of aggregation switches, right? And then that all connects up to probably a core network, and then you have the data center switch, and then you have a server sitting beside in the data center, right? A very typical enterprise network, and on the bottom you have the host, right? I've just simulated the host using routers, but yeah, this is basically your laptops and phones and wired and wireless clients, right, which is on the bottom. Okay, now what do we want to do here is that, or the problem what we have is, imagine a network where until here, right, you're going to have your V6, right? And imagine above you're going to have your V4, right? So when I say we have V6, I mean to say we have enabled only V6 here, we have enabled only V4 here, right? Now this creates a problem, because if you're sitting somewhere in this network, you're probably on your laptop, you would have gotten only a V6 address. So from a V6 host, you can't really talk to this this V4 only server, correct? Because a V6 is IPv6 is a different stack when you compare to IPv4, right? So that's the problem which we are trying to solve in this one. Okay, so if I want to kind of simplify this, what do we have? We have a IPv4 here on the top. We've got IPv6 here on the bottom, right? We are in search of a translator, and that is basically NAT64. That is the topic of discussion today, right? So the NAT64 is the device which will basically convert this V6 packets to V4 and vice versa, from V4 to V6, right? It will facilitate the communication between these two. Okay. Now technically this solution is not just NAT64. You'll normally have one more piece in this puzzle, which is called as DNS64. And I'll obviously we are not going to be using DNS64 in our topology as such, but I just want to put it out there so that I can give you a complete picture of the solution, how it really works, right? So this is how it works. And generally you have your so DNS64, just to give you an idea, it's nothing but a forwarder, right? It's nothing but a DNS forwarder, right? I'll not get into the very in detail DNS technology, but I think it's basically a DNS forwarder is a very common term, right? So I think it's pretty simple to understand that. So we've got DNS forwarder. DNS64 just acts as a DNS forwarder, which means that it should actually forward the DNS request to someone else, which is the actual DNS recursive servers, right? Your organization will have it, right? Most of the organizations are going to have a DNS server, or it can be even, say, the Google's DNS servers, which is 8.8.8, or it can be umbrella DNS servers as well, right? So this is the whole solution. So what happens? You are sitting here, okay? You're sitting here inside the IPv6 network. You have your laptop on, you have your Android phone or your iPhone connected to the network, and the devices are just getting IPv6 address, right? Now you want to talk to something which is sitting here, right? Let's call that as example.com, right? So you want to talk to this guy, you want to talk to example.com, but the problem, this guy has just V4, you have V6. How can you establish this, right? How can you make it work, right? Typically in an enterprise, or typically a majority of the traffic which is going to be generated is what? Web traffic, right? So the very first thing you're going to do when you have to talk to example.com, DNS, correct? So in IPv6, what type of DNS do? We do a quad A query. Quad A, right? Quad A query is basically a request which you make towards your DNS asking for, hey, I want to talk to example.com, can you give me its IPv6 address? Now this DNS64 will promptly forward that request all the way to your DNS server, and the DNS server will reply back saying, unfortunately, we don't have the v6 address because this guy has been enabled only with v4, right? And you might ask, okay, why do we even need to look at this solution if we can go and dual stack this server, right? This particular application or server or whatever it is. True, right? If you have dual stacked it, great. Then you don't really need NAT64. But there are many applications out there, many servers out there which probably don't support v6, right? Or the application will not support v6. So in that case, you still will need to use v4, right? So this is a solution which will mainly come into come handy over there. Okay. Cool. So coming back here, you're sitting here, you're trying to talk to example.com, you've made a DNS query, the DNS64 has forwarded to the actual DNS, and the recursive DNS server has replied back saying, look, I don't have a v6 address for you, I'm sorry. So the DNS64 which is sitting here will fabricate a v6 address for you, right? That's the cool thing which it is going to do. That's the main job, right? Because it is not going to resolve anything for you. Whatever resolutions you are going to request from it, it is just going to forward it to the actual DNS server. But what it is going to do is, when there is no IPv6 address, right, and there is only IPv4 address, so this DNS server will reply back saying, look, I don't have a IPv6 address, but I have a IPv4, right? To make it interesting, let's probably give it an address. Let's give it 10.1.1.1, right? A typical address, 10.1, right? So this DNS64 is a bit intelligent, right? What it is going to do is, it is now trying to fabricate IPv6 address, right? This is interesting. So in order to fabricate, IPv6 address has how many bits? 128, correct? And we also know what? Currently we also know the IPv4 address of the server, which is 10.1.1, right? The DNS has given that information to us. So we are still in search for what? 96 bits, 96 more bits, because 128 minus 32 is 96, right? So we still need 96. So what this guy is going to do sitting here is, it will formulate or it will fabricate a IPv6 address which will be of this sort, right? The first 96 bits, and it will basically take this 10.1.1.1.1, right? So this 32 bits, it will convert to hex format and it will use it as the last 32 bits. But for the first 96 bits, it will use something which is stored inside it, right? There will be a prefix which is generally stored inside it or configured in it, right? It can be anything. It can be something like 2001::100::, right? There you go. That's a /96 octet, right? So that is how the DNS64 creates this IPv6 address, right? Creates this illusion to the user sitting here that, hey, this example.com has a v6 address, right? Though technically there isn't, right? But it is going to create that illusion. It is going to give you a reply back with this particular address, right? So the user sitting here will have the address. What is the address now? 2001::100::, and the hex version of 10.1.1.1. What is it? I believe 10 in hex is A, right? So it's going to be A. 1 is going to be 01, right? Then you have 0101, right? So there you go. That's the IPv6 address, right? This is just hexadecimal conversion, right? I didn't do anything. A is basically 10 is basically A, right? 1 is 1, 1 is 1. All of these are going to be 1, right? So I just did the conversion here. But that being said, the user sitting here gets the IPv6 address, and now he can basically form a packet. He can basically create a packet, right? And send payload towards the example.com, which is great. Packet arrives on the NAT64, right? The NAT64 which is sitting here will, what it will do? The packet or NAT64 will also be configured with the same prefix. That's where it gets interesting, right? So this prefix 2001::100. Also, I'm using this prefix here. It doesn't mean that we all have to use the same prefix. You can use whatever prefix you want. I'm just giving an example. But whatever is this /96, right? The first 96, that will be configured here as well. Use my pen. So it will be configured here as well on the NAT64 side. So when it sees any traffic to that destination, it understands that it has to get to work, right? What will it do? What's its job, right, to begin with? It has to just convert v6 to v4. It has to facilitate the communication. So what it is going to do is, as soon as it sees this packet, it will strip off the v4 part, which is only this one, correct? Which is 10.1.1.1. It will strip that off and it will create a new packet here, right? That is the translation what it is doing. So it will create a packet with the source address being the destination address being 10.1.1. Let me actually get rid of that. Let me correct it. Don't want you guys to get confused, right? So a packet will have what? A source address and destination. The destination is going to be 10.1.1, right? So it is basically going to strip it away from here and it's going to use it here. Okay. Now you might ask, okay, what is going to be the source address, right? What is this going to be? Use a different color. What is going to be the source address, right? Now that's where we can that's again configured on the NAT64, right? That's again configured on the NAT64. So again, you have different ways of doing it. You can do static, you can do dynamic, you can do pat, right? If you are doing static, then what you would end up doing is every single host which is sitting here will have a corresponding IPv4 address, because to talk to the IPv4, I need an IPv4 address. Correct? It can be something like 10.2.2.2, right? But that will be configured on the NAT64 and I'll show you that, right? But don't worry about this for a minute. The source address will be configured on the NAT64. We will instruct the NAT64 to use either a single address, either a static address, or to use a pool, a dynamic pool like we do normal NAT, or to use PAT, right? So that is something which we are going to look at. But you get the whole fundamental idea here, right? So now that once you have a IPv4 packet, the packet is going to go all the way to IPv4 world. Example.com is going to look at it. It is going to respond back. Now when NAT64 again sees a packet with this 10.2.2, it understands that, okay, I know this address, and it is going to reconvert it or translate it back to this IPv6, right, towards the IPv6 side, right? So, and then the communication goes through, right? So that's how this whole NAT64 and DNS64 sits in the middle, and it is able to facilitate the communication between your between your v6 and the v4 worlds. Okay, hope that was clear. All right, so I just cleaned up my whiteboard. So now I think, now that we have a bit of idea about how this whole NAT64 works, let's actually get to the configuration and let's play around with it and kind of understand a bit more along the process. I will obviously be sharing the lab as well as the configurations for all the devices on my GitHub repository, right? You will find that on the on my YouTube channel. On the right hand top corner, you will find the link on the banner. You will find the GitHub link, and you can download everything from there, right? So okay, let's get to it. Okay, but before we get to the configuration, let me actually take you to the documentation, right? This is all publicly available, right? Cisco's documentation, it's available. I'll probably I'll paste the links of this in the description as well, right? But all the documentation which I'm referring to is available here. On the left hand side, you can see you have Stateful NAT64. Then we have something called as Stateless NAT64, right? There is that second one, and so you have stateful, stateless, and the other one which we'll be looking at is the interchasis redundancy. So all of these three concepts, right, we'll put together and we will try out the lab, right? Cool. Yeah, so yeah, I think we're good to know. Just a quick point here would be that I mean, we just talked about NAT64. You might have a question about what is stateful and what is stateless, right? And I think the names are self-explanatory, right? In stateful, what really happens is the NAT router will create a entry, right? As soon as the first packet hits the NAT64, it will create an entry telling that, look, this is the session. It will create an entry per session or per flow, right? and that entry will have information about what is the source address, what is the destination address, what are the ports they are trying to talk to, and so on. Right, so the advantage of this obviously being in case your primary router goes down, what you can do is you can quickly force the traffic on a secondary router, and you can exchange this information. This whole state table can be exchanged with the secondary router, and the secondary router can pick up the traffic. Right, so it gives you the capability of doing that redundancy. Right, and that redundancy is what we are going to explore using this thing called as interchassis redundancy. Right, so the stateful NAT64 and the interchassis redundancy are very tightly coupled. Right, they are very tightly connected, because the reason why most of you do stateful NAT64 would be to then use interchassis redundancy to bring in some redundancy, because if your primary router goes down or one of the interface goes down, you can quickly switch over. Automatically you can switch over to the other device which is well and healthy. Right, then we will also look at stateless. Right, stateless NAT64, like it's evident from the name, you don't create any state. Right, here as the NAT64 router gets the packet by packet, it will do the translation. Right, and generally what you do here is the IPv6 addresses which you need to use in your IPv6 side of the world will need to embed IPv4 addresses. Will need to have embedded IPv4 addresses, and I'll talk about this when we do the configuration. Don't worry much about it. But for now, just remember, stateful, you create a table, you keep that information in a table so that you can then use that information to give it to a secondary router and then kind of bring up redundancy. Whereas in stateless, obviously you can't have redundancy off the box. But I will actually show you a very nice configuration which I have put together here using a bit of HSRP and so on, like some fun stuff. And we will see how how optimally you can do NAT64 in an organization. Right? Cool. Let's start. So we have, like I said, we have this topology. Right? The topology I will be sharing. I mean, it's a free. It's nothing. I mean, you can create your own topology as well. I just have one access switch, one distribution switch. Couple of aggregation switches. I have a data center switch, IPv4 only host. Right, this is signifying that this particular host just has IPv4 address, and then you have two endpoints here to signify the two types of use cases which we are going to look at. One is the stateful NAT64, other one is the stateless NAT64. That's why you have two end hosts here. Okay, all right, so I'll actually not go in detail about rest of the configuration. I'll probably give you a quick understanding of what I've done. Right, let me actually get my pen over here. One sec. Yeah, so before we get to the configuration, what's our game plan here? What do we have? Right, so let's start from where do we want to start from. We'll start from bottom. Right, so this is my distribution switch. So in my distribution switch, I have two VLANs. Okay, one is VLAN 20 and the other VLAN is VLAN 10. Right, I've created two separate VLANs because I wanted to separate these two use cases for stateful, and so this is VLAN 10, I believe, is for stateful. You can we can check the configurations, but VLAN 20 is for the stateless. Right, so I have created two VLANs, created two SVIs, and obviously I have trunked this particular link. Right, this link is trunked. Right, very evident. Right, because we have two separate VLANs. So once I've trunked that, obviously I have put these this particular interface in VLAN 10 and this particular interface in VLAN 20. Okay, this is all typical L2 access traditional 3-tier architecture. Right, nothing fancy here, straightforward. Other point to keep in mind is that till here, right, I have only IPv6. There is no IPv4, purely IPv6. Okay, so these two VLANs are just enabled with IPv6, right? And I have enabled that. I've enabled those VLANs in IPv6 and I have advertised them in a IGP. I think it's EIGRP. Okay, so till here we are good. Actually, let's actually look at the configurations quickly, right? Since we discussed that, I don't know which is my switch though here. Okay, there you go. So this is my distribution switch. So what we'll do is show run interface VLAN 10, right? There you go. So it has IPv6 address, and I've enabled the EHRP on it, right? And the other VLAN is VLAN 20. Okay, pretty simple, right? As simple as that. Good. So we are good till here. Sorry, let's come back here. Next, what we do, so on this aggregation switches, right? So we will not talk about NAT64 for a minute. Let's talk about the complete underlay. So on the links connecting the aggregation switches to the data center, that is what IPv4 enabled. So this is V4. This one is also V4, right? So this one, these two links are V4 enabled, right? Very much with our use case, what we want to present today, right? We have V6 below, we have V4, that's our use case, right? We want to talk between V6 and V4. So that's why this is what has been done. So, and then obviously this one is also V4. Okay, so this is a host. Typical V4, I can show you that on the, maybe let's look at it on the DC switch. Where is the DC? This is probably the second one. Yeah, there you go. So maybe let's do show IP interface brief. Right, there you go. So it's only, you can see these are point-to-point links connecting the, these are the two point-to-point links connecting the aggregation switches, and this is the VLAN which is connecting the IPv4 only host, right? There is nothing IPv6 on it. I can double interface brief. I'll show you to you here. There you go, right? It's empty. So there is no IPv6 at all at the top. Perfect. That's what we want. Okay. Now this is where we have to bring in our NAT64. Correct? Let's actually clean this up a bit. Give me a second. Let me clean this up. Okay. So NAT64, right? So this is actually a physical topology, but to explain this better, I think it will be helpful if I create a logical topology, right? So I have everything on the IPv4 side on the top. I have V6 at the bottom, right? I have the NAT64 here, like this, right? Now the logical topology here is, what I have done is I have created two VLANs, okay? One VLAN is called as 640 and the other one is called as 641. Okay, I think it's reverse. I believe it is 641 below and 640 on the top. Okay, there are two VLANs, right? So VLAN 641 is basically, think of it as the inside VLAN, right? 641 is the VLAN through which you are going to get the traffic from the V6 world, right? Whereas 640 is the V4 VLAN, because you're going to get the traffic from the V4 world, right? Or you're going to send traffic to the, basically it's a V4 enabled VLAN. This is a V6 enabled VLAN. Okay. Now underlying, if you look at the dig into the configurations, what you will actually see is, on each of these, I have also enabled HSRP. On 640 and 641, I have enabled HSRP. Why I have done that? To kind of get us some redundancy, right? So these two SVIs, they are actually first sitting on what? On this layer, right? On the aggregation switches here. Okay. So we have both 640 and 641 on these both, and we also have HSRP, right? So because of that, now what I'm getting is I'm getting redundancy at this layer, correct? I'll show you that. Let's get to the aggregation switches and let's look at that. So let's come to, okay, there we go. That's the aggregation switch. Okay, so let's look at show standby. That's how you see the HSRP, right? Show standby VLAN 640. Perfect. So you see on the VLAN 640, I have HSRP. This one is the active. Obviously, the other one will be the standby. You can see it has a virtual IP and a virtual MAC address and so on, right? So this is the 640. This is the V4 VLAN. There is also a V6 VLAN, which is 641. And that's basically nothing but the V6 VLAN, and there also you have HSRP. Why this has been done? Obviously, to provide redundancy at the aggregation layer. So even if one of the aggregation box goes down, we will still have the other box up, right? So that it will be able to forward the traffic. Okay. So that's one thing. That's one thing to keep in mind, right? So we have 640 and 641. These are very These are two very important VLANs. Okay. Now, while we are talking about VLANs, let's also talk about there's actually two more VLANs, which is 648 and 649. You'll actually find all of this, in the configurations which I will be sharing. But I don't want you guys to think, okay, what are these VLANs when you look at the configurations, right? So there's also 648 and 649. And we will actually get to it in a minute when we actually do the configurations, right? Don't worry. But yeah, all right. So I think this much context is good before we get to configuration. Maybe let me also spend one more minute on the guide again. Let's actually get to this section. Which section? The interchassis redundancy, right? I just want to cover this before we get to the configuration, because if you guys haven't heard of this before, it's not a very new topic, or it's not a new technology. It's been there for ages, right? People have been using this for NAT. People have been using it for firewall and so on. But if you haven't, right, give this a read. But to probably like a 50,000 a view of this particular topic is that interchassis redundancy, right? It basically gives you redundancy at the interface level, right? So in this diagram, what you see, you have two devices, right? Basically, these two devices will be our NAT devices, right? In my diagram, if you see, we have NAT gateway 1 and NAT gateway 2, or NAT64 1 and NAT64 2. So we want to establish redundancy at the NAT64, and we do that using interchassis redundancy, right? So these will be the two devices, and this is a protocol which has been there since ages. You use it for NAT and use for firewall and so on. But the idea here is you generally create what we call as an interface group, right? What is depicted here, with this diagram here. So you have a group A which has been created here, correct? And once you create a interface group, it will basically have a bunch of redundant interfaces, right? So that group will have a bunch of redundant interfaces. Like in this example, if you see, what is happening is that you basically have two devices, router 1 and router 2, and you can see both the router 1 and router 2 is connected to some device on the top and some device at the bottom, right? So you want some kind of redundancy, don't you? So if one interface breaks here, you want the traffic to go through the other one, correct? Same thing on the top. When one interface breaks here, you want the traffic to go through the other one. So have some kind of a standby, right? Basically, it's nothing but HSRP on steroids, right? As simple as that. What does HSRP give you at the end of the day? It's nothing but a redundant gateway, right? It's a way of configuring redundant gateways. So if one of your gateway goes down, the standby will pick it up. The standby will pick up the traffic, right? Very similar to that, except what this brings to the table, or this configuration, or this technology, or this feature brings to the table is, in addition to the router 2 picking up the traffic, right? Say router 1 goes down, or one of the interface goes down, the router 2 will pick up the traffic. But it will not just pick up the traffic, but you also have a provision to exchange some information between them, right? Now that's where it gets very interesting, because we spoke about stateful NAT64, correct? In stateful NAT64, the router is going to have a table which will have information about the states, about the NAT64 states, about the translation information. Now, when you use stateful NAT64 in conjunction with the interchassis redundancy, what you can do now is, if your primary router goes down, you can exchange that state information using this data link which you see. You can send it all the way to the other device, and boom, your second device will now start functioning. Now it will now forward the traffic, which is great, right? We are getting NAT64. In addition to that, we are getting redundancy at the NAT64 layer, right? That's what it gives us. So that is where I was going to mention that in addition to the VLANs 640 and 641, we also are using two more VLANs, which is 648 and 649, right? So that is basically 648, I believe, is used for the control link, and other one is the data link. These are just pure L2, links, right? They don't need to be routable. They can be directly connected links. But they just need to be there so that the devices can exchange hello packets and the data information, So hope that's clear. That's basically nothing but 648 and 649 in our topology. But this is what we are doing, right? So this is something which you guys can have a read at. It's pretty nicely documented here. But this is what we are going to be using in our lab, right? So coming back, I think we have all the pieces of the puzzle ready. Like I said, I have done all the routing part, right? In this video, we will just be configuring only the NAT gateways. I have already done the HSRP and all of the stuff which from the routing perspective, so that we don't waste a lot of time. So we will just be configuring the NAT64 1 and NAT64 2, right? We will do the stateful first and then we will do the stateless. All right, so let's get to the topology here. So we are going to, like I said, we're going to configure NAT64 1 and NAT64 2. Okay. First things first. Again, all the configuration what I'm doing, you will find it in the guide, very nicely explained. But yet I'm going to do it now. Okay. So let's get to NAT64 1. Okay. There you go. That's my device. Doesn't have much as of now. Let's see what it already has. Probably it has just IP configuration, show IP interface brief, and let's also probably look at IPv6 interface brief. Okay, that's what we have. Now I've explained this in my previous videos as well. It's a bit difficult to get CSR 1000Vs to work with the sub interfaces, right? This is like a workaround, right, to get VLANs and encapsulation, all of that to work by using BDI, right, bridge domain interface. I've actually touched about this in my previous videos, but for people who haven't seen those, a quick issue or the quick description of the problem here is that on a CSR 1000V device, when you're trying to simulate it either on EVNG or GNS or CML, wherever, right, you will sometimes find an issue where it doesn't work well if you create sub interface on this side, right? Because see, this is a switch, so I've put a switch here and all these links are nothing but trunk links, all right? And my NAT64 typically is supposed to, ideally in my production network, I would basically go and put sub interfaces, right? Especially on devices like ASR 1Ks and so on, because it supports sub interfaces. CSR 1000 also supports the commands, but especially on this emulated tools, it doesn't work that well, right? So something which works is by using bridge domain interface. And how you do that? Let me show you that. Show run section interface. Right, so this is how you do it. So this is my interface, right, gig 1. So what you do is you basically create a service instance. So these are all the 4 VLANs which I spoke about, right? 640, 641. 640 is the IPv4 one, which is towards the outside, right, of NAT64. This is the inside of NAT64. And you've got the rest of the 2 VLANs which are just mainly for the control and data communication for the interchasis redundancy, right? So this is how you create the service instance. And once you create the service instance, you can then use what we call as bridge domain interface, right? Interface BDI. So this does the same job of what? Sub interfaces, right? That's it. I mean, if sub interfaces is working for you, go ahead, use it. If it is not, then resort to something with what I've done here. But the basic funda is still the same. You put trunk on one side, you put sub interfaces on the other side, and get it working. Okay, cool. So that being said, step number 1, what we do is, remember we talked about interchasis redundancy. So we need to configure the interchasis redundancy, right? So let's get to it. So how you do that is, let's clear the screen a bit so that it's visible. I'll actually paste the configuration and I'll explain to you because I don't want to type it out and waste a lot of time. I have the configurations handy here. All right, so this is what we're going to do, right? So redundancy. Now, the redundancy, what we are going to establish here, the interchasis redundancy, it's actually called as application redundancy, right? Because you don't really need the whole box to go down for the switchover to happen, right? It's at the application level. That's something which we need to understand, right? So that's why when you configure it, you do it under the hierarchy of application redundancy, right? Then you create a group, right? This is that redundancy group which I talked about, right? So if you generally, I mean, if you don't have a multi-homed network you stick to only one group. But if you have a multi-home network, then if you want to create multiple redundancy groups, you can do it as well. The provision is there on the router, you can do it. But in our case, we are basically going to use a single group, right? So this is a unique identifier and this is a unique name for that particular group, right? And I'll show you where we are going to use this, right? Because what we are trying to do is, if you go back to this diagram, right? So this is just when you're configuring it, just look at this diagram, right? This will help. So what we are doing, that the group configuration is basically this one, right? The group. And you can see in this group, we typically have two sets of interfaces. So you have one set of interface on the top and one set of interface at the bottom, right? Very similar to what we have as well. We have 640 on the top and 641 at the bottom, right? That's exactly what we're going to do. Okay. So we have one group. You can just have one group, name of the group. Preempt, very typically like your HSRP preempt it is. So, it allows the router to preempt and kind of assume the active mode, right? If it comes back up. So you can draw a parallel with HSRP, right? It works very similar to HSRP. You have active standby, right? One router is always forwarding, the other one will be standby. And this is how you give the priority, right? On this one, we are going to make it primary, or we are going to make it active. So that's why we are going to give the priority of 110. Timers delay 10, 20. So what is this? This is basically, again, good to have configuration, kind of like an optional configuration. You don't really need to have it always. But what it really does is, if the router goes down, right, it waits for it waits for like 10 seconds before the switchover happens, right? Because there are many scenarios in the network where the switchover would have happened before the underlying network would have converged, right? And that can create a lot of routing issues and a lot of suboptimal issues in the network. So this is basically giving 10 seconds before the switchover happens, right? And reload 20 basically comes into effect only if the router goes for a reload, right? But basically we are saying do the switchover redundancy, or do the switchover only after 10 seconds so that we give enough time for the underlay to converge. Then we have to mention the control links and the data links, right? I mentioned the VLAN 648 is for the control link, right? That's how the NAT gateway 1 and 2 are going to talk to each other, right? And send this control messages, right? And the data link, obviously 649, the other VLAN is the one where they're going to send all the translation tables, right? So in case there is a switchover needed, right, the translation table can be sent to the other side and the other router can pick up the traffic, right? Protocol is just it's basically nothing but a instance of it's just an instance number, right, representing the control protocol, right? Again, like I said, if you're using one group, right, typically you can just use, I think the protocol numbers go from 1 to 10 or 8. You can use any number. It's just a unique identifier for that particular control protocol, right? All of this becomes significant in case you're having multi-home networks where you are going to create multiple groups, right? So if you're creating multiple groups, then you would want to use different protocol numbers for different groups, right? So if you have multiple groups of interfaces you want to create redundancy for, then go ahead, you do it. But then you can use multiple groups. In this case, it's going to be just the same group. So we are just, this again is an optional configuration. We are just calling out the protocol number and then attaching the redundancy group name to it, right? Cool. So that's it. Let's put that in. Let's also do that on the standby or the second router. The only difference here, let me call out and let me paste that. Let's go to the second one, which is this one. Right, the only difference here is everything is same, only the priority is going to be reduced here. It's only 100. It was 110 earlier, it is 100 because I want this router to be my standby. Great, so we have gotten the redundancy configuration all done, which is good. Okay, so awesome. You can see it's already doing the whole election and it is trying to figure out who should be active, who should be standby and so on. Looks like this guy has picked up the active and maybe in some time the other guy will pick up as the, there you go, it already went to standby. I'll quickly show you the show commands later, but let's move on. So we are done with the redundancy configuration. The next is we need to configure the interfaces, right? Let's do the outside interface, right? When I say outside interface, let's go back to a diagram, this one, the 640. 640 is the interface which is connecting the NAT gateway to what? To the v4 world, right? Let's configure that. Right, so what do we already have on the interface? Let's look at that. Do show run interface VLAN 640. Okay, sorry, it should not be a VLAN, it is VDI, correct? 640. There you go, right? This is what we have, right? So we have an IP address and we don't have anything else apart from that. So what we are going to do is, let's get into that interface, okay? And we have to enable NAT64 on this, right? So what is the command for enabling NAT64? NAT64 enable, as simple as that. So this command will tell the router, look, there is the traffic which is going on this. You need to keep a watch out for, because you're going to get traffic which is destined to what? To be translated, right? This is what tells, this is the significance of that command, right? And remember, we talked about this whole redundancy, the whole reason why we did this whole redundancy, right? There's no fun if you're not using it, right? So we need to use it, and we'll be using it now, right? How do you use it? For each redundant pair, right? In our case, we have two sets of redundant pairs. One is VDI 640 and the other one is 641. For each redundant pair, you need to use a unique identifier, and that unique identifier you configure using redundancy RII1. So 1 is the unique identifier. It has to be the same on the other side as well, right? That's good. And once you configure the unique identifier, we have to map that unique identifier to what? To the redundancy group, right? The group will still be 1, right? In our case, we are using only one group, right? So we have to map it to that, right? And the other point, I think you might ask a question, in HSRP, when we configure HSRP, what we do is we have a virtual IP, right? Is there a provision to do that? Yes, there is a provision to do that here. So this is basically going to be the command redundancy group 1, right? So we are attaching this interface to the redundancy group 1. This is the virtual IP 172.16.22.4, right? And exclusive decrement 20, right? I think it's again self-explanatory, right? What does this mean? We are basically providing a weightage, right? So if there is if someone goes and, or if this interface breaks, right? If there is a physical issue with this interface, we want the switchover to happen, right? So we are giving it a weight of 20. So every time this interface goes down, the priority goes down by 20, right? What is the priority? See here we have configured 110. So every time this interface goes down, the priority goes down by 20. So once it goes down, the priority goes down. It says it will go down to 90, then it will go down to 70, right? And you see we have configured a threshold here. So when it goes below the threshold, that's when the failover happens. You see how all these commands are like interrelated? Exactly. So if you do once, if this interface flaps once, right, the priority goes down, and the failover can happen, right? So that's the whole meaning of that. Okay. Give me a second. All right. You can decide whatever you want, right? You can keep this to 20, 50, and whatnot, right? Yeah, that's my net. I mean, in my case, if you look at it, right, I just have what do I have? I have this BDI, all of this is virtual interface, right? This virtual interface is never going to go down. That's why I've put it as 20, right? I mean, I just want to give you an idea into my thought process, right? Why do I put it as 20? Because in my case, it is just a virtual interface. The only possibility of a breakdown in my network is if the physical interface goes down. What is the physical interface? Here, let me scroll top, this one, gigabit 1. So if this interface goes down, right, then what will happen? My priority will go down. My priority will go down twice. It will go down once for this for BDI 640, and it will go down once again for 641. So the priority decreases by 40, right? So 110 minus 40 is what? 70. So 70 would mean that I have to fail over, because 70 is lesser than 80, so it will fail over. So that's my thought process of using 20. I just wanted to put it out there. You can use such kind of logic to figure out what you want, right? What kind of decrement you would want. Okay, sweet. Now the same configuration would go on the other side as well, right? Very similar to HSRP, guys. Nothing very complicated, right? Let's do that. Awesome. 640 is done. Let's do the next interface, which is 641. Now that you have a hang of this, let me quickly paste the configuration without much fanfare, right? So we have BDI 641, which is the V6 interface. We are again enabling NAT64 because this is the inside interface, right? Just like how you enable NAT, right? NAT inside, NAT outside, very similar to that. Here the command is simple. You just need to say NAT64 enable. Observe the identifier, it has changed from 1 to 2 because it is a new set of interface, right? This is 641, so that's why it's a different identifier. And then we have the very similar, except the difference here is this is IPv6. It was IPv4 because it was 640. It is IPv6 because it is 641. Let's go, paste it. Let's do the same thing on the other side. Paste it. That's on done now on both the sides. Okay. That's good. So I think we are now good to do the what? The NAT64 configuration, right? So for NAT64 again, let's do it on the primary first. Let's clear the screen a bit. Okay. So for NAT64, right, step number 1, remember that /96 prefix, you need to have that ready. In my case, this is what I'm going to use. I'm going to use 2001:55::96. That's the one which I'm going to use. You can use anything technically, right? I'm using this. Next, I would be showing you what? I will be showing you actually PAT, right? I'll be showing you NAT64, but the PAT version of it, right? So that's why I need to have some kind of a pool, right? Because when you create a PAT, when you configure NAT64 with PAT, you need to provide a pool of addresses NAT64 can use to do the translation, right? So this is going to be my pool. What is my pool? Okay, I did not copy it. Give me a second. So my pool, there you go. My pool is basically 10.1.1 all the way to 10.1.1.254. These are the addresses which we are going to use, right, which the NAT64 is going to use in the IPv4 side of things, right? Because the packet coming from IPv6, it has to finally go to v4. So when it goes to v4, you need a source address, right, for the packet to be formed. So this is the set of addresses which will be used, right? We are providing a big range here. Technically depends how big your size of the network is. Based on that, you can decide the range. Now the most important command is where all the magic happens, right? Which is nothing but, okay, it got copied. Maybe let me just paste it down here just to explain to you guys, right? This is the command. So we are going to say NAT64 v6 to v4. That's what we want, right? The translation. We also can provide an access list. So I actually have an access list, right? I think it's already on the device, but it's not mandatory, right? But what is the access list? Access list will basically decide the subnet from where the traffic is going to come. In our case, what is the subnet? Go back to the diagram. VLAN 10, right? This is the VLAN 10. This is the subnet from where the traffic is going to come, which has to be translated. So I have just put that you can see the configurations once I provided to you. But that's the that's the subnet which I've added in this ACL. Okay, and then you have the pool which we just now defined. I'm mentioning the pool, right? And then you have overload, which tells that we have to do PAT, and then the redundancy part, right? Because we are doing interchassis redundancy. This is how we are tying up NAT64 to interchassis redundancy, right? This is basically redundancy. This is the redundancy group. This is my local group, and I'm mentioning what is the group on the peer, on the standby, which is also 1, right? And I believe technically this you have to use the same group on both the sides, right? There it goes. That's the command. Let's put the command in. There's another small caveat here. If you want the HTTP traffic, right, to be replicated on your standby, you need to put one more extra command, which is very specific. NAT64 switchover replicate HTTP enable port 80. So this will basically make sure that any of your HTTP connections also will get stored in the translation table and sent to the other side or replicated while the switchover happens. All right, that's good. Okay, so that's mainly it. I'll not again show you all the routing and all of that because it will get very complicated because it's a pretty big topology, right? I'll keep all of that for your reference in the configurations. But I think that was mainly about the NAT64 side of things. Okay, now let's actually quickly go and do it on the other side as well. Right, so the command actually, yeah, remains the same. There's no difference at all. All these 4 commands will remain the same. So let's go and quickly put it. Okay, so those are the 4 commands. Are we good? I think we are good. We are good to now test NAT64, guys, at least the stateful version. All right, so to test it, what I'll do is, so let's go back to topology just to explain to you what I'm going to do. So to test it, I'll be on the stateful host, right, which is on the left hand side here, and my whole objective is to do what? To talk to this IPv4 host which is on the outside. Okay, so let's first go and find the IP address of that IPv4 host. This is the IPv4 host. So what's the IP address? Show IP interface brief. Okay, there you go. That's the address. Now we need what? We need that translated address, right? The one which DNS64 would have given us. Right now I don't have DNS, so I'll have to manually get it. How do I get it? A simplest way I do is I just open terminal, right? So you open terminal, just put ping 6. What is your prefix? Your prefix is 2001 colon, I believe it's 55, right? Colon, right? This is literally what I want to do, right? This is what my DNS64 would have given me, right? So it would have given me the /96 and then the 32 bits at the last. I'm going to hit enter, and this is a neat trick, right? The terminal will give you this address. There you go. Right, so I'm going to just take that and I'm going to, so I'm going to go back to my stateful host, which is this one, yep. So I'm going to go here and let's do a ping. All right, there you go. It's working, right? Quickly, let's actually do an elongated ping. Let's do a ping. Let's repeat this for say 1000 or maybe more than that, right? So the ping is going on. Meanwhile, let's go to our NAT64, which we just now configured, which is probably here. Let's do show NAT64 translations. There you go, right? You can see this is exactly what we are trying to do, right? So we have, this is 2100:55::10 is nothing but my the stateful device, right? So that's my, I don't know if I have my, okay, I'll probably show it to you in a minute, but that's my source address of the stateful device or stateful host. And look, it is trying to talk to what we just now did, right? 2001:55 AC 10.101, and this is nothing but 172.16.1.1, which is nothing but this one, right? Pretty cool, isn't it? So we are now able to talk between the v6 and the v4 words, right? So, and you can see this is what I was talking about, the translation table. So because it is stateful NAT, you can get all the translation entries in the table, right? And you will not get this when we do stateless, which I'll show you in a minute, right? But this is good. The second thing which I also want to show you is the whole benefit of doing redundancy, right? So let me show you that. So let's come back to this NAT device. Let me probably clear the screen, right? And I can use command like show redundancy. Let's show redundancy application group. I believe it is 1, right? So application group, remember this is the redundancy group, and you can see what has happened here. It is telling that this device is active, right? This device is active, the peer is standby, right? So now what I want to do is show IP interface brief. Remember the interface, or actually let me clear the screen. Let's see what is the interface. Show CDP neighbors, right? CDP is not available, but basically the interface on which we have everything is the gigabit 1 interface, correct? Show IP interface brief. This is the one, Gigabit 1 is the physical interface on which we have these BDIs. What I'm going to do is I'll just go and shut this down. Right? So let's go and shut this down. Right? Or yeah, I can probably do that. So I'll go and shut it. Right? So as soon as I shut this, what we should see is we'll probably see a couple of ping drops here. But then the secondary should pick it up. That's my understanding. So let's go and check it if that works. So I'm going to hit the shut. I did that and there you go. There's a ping drop. A couple of them dropped. 3. Okay. 4. There you go. So the ping drops and then you can see it has picked up. The reason is because the standby picked up the traffic. There you go, right? The standby became active. Now I can do a no shut here. If I do a no shut, ideally within few seconds, it should again it might have probably a couple of ping drops, I guess. But then because we have configured preempt, what it is going to go, there you go. See, the ping drop is starting. But because we have configured, there you go, 2 ping drops and then the packets again started to go through, right? Why this happened is because we have configured the primary device or the first NAT gateway to preempt. So because it came back up, right, what it did was it went and picked up the traffic. We can see a little bit more detailed output as well. Show, I believe, redundancy, application group, all, I believe, if I'm not wrong. Yeah, this one gives a little more information. You can see the runtime priority currently is 110, right? So because the interface came back up, the priority went up to 110. Okay, so that's how simple it is, right? And all of this is possible because we did stateful NAT64 with interchassis redundancy, right? So even if one of the device went down, one of the interface went down, we were able to redirect the traffic towards the secondary, and then we saw that the packet drops were very minimal, right? Within like probably 5-6 packets we were able to get back up. Okay, cool. So the last part which I also want to talk about is the stateless NAT64, right? For that, let me just pause for a minute and clean this up. All right, so before we go to stateless NAT, right, I will actually give you an explanation on when I would use it, right? So if you come back to our translation table here, which we saw earlier, where is that? Okay, there you go, right? So this was the translation table, right? Now you saw here what we did was, in our example, we did overload, we did pat, correct? But in addition to that, if you just remove this word overload, it would end up being just dynamic NAT. Then what would happen is, for every connection, for every flow, right, NAT64 would basically use a different address in the IPv4 world, right? Here you see it is using the same address, 10.1.1. It is using for flow number 1 and for flow number 2 it is using the same address, but it is using different ports, right? That is what PAT does, right? But you see, this will not really fly if I have some connection originating from IPv4 to v6, right? What I mean by that, if I look my diagram here, this will fly or this will work only if the connection is initiated this way, right? Because if the connection is going from v6 world to v4 world, then I can obviously use different ports on that same address, which is 10.1.1.1. I can keep on using different ports and the connection will go through. But if I have a connection originating from v4 to v6, say something, sitting here, maybe a management server wants to talk to some endpoint which is sitting here, right? So it is initiating a connection. Then this will not really work, right? Because these ports, right, are very, you can't, these ports are very, they are not static, right? They will obviously change as soon as the connection is dropped. So it will not, they are not persistent, right? That is why in the NAT world, that's why we have 3 different types of NAT, right? We have static, we have dynamic, we have PAT, right? We use static NAT mainly for this purpose. When you have some traffic, when you have someone from the outside trying to talk to you, right? That's when we use the static NAT. Okay. So yes, now in stateful NAT64 we have static NAT and it is possible to configure it. But the downside is that you have to literally sit and manually configure each and every address, right? So each and every address, I mean, if I come back to my topology, what I'll have to do is I'll have to go and configure each and every, I'll have to put the commands as NAT64 blah blah, and I'll have to configure that, look, 55:10 should use 10.1.1, maybe a different address should use another address, right? So maybe 10.2.2.2. So I'll have to manually configure those entries. Now imagine if you have an enterprise with probably, I don't know, maybe 50 or 100 endpoints needing that kind of a situation, right? It's not very good because you have to literally sit and configure probably 100 entries, right, on your router, which is not very good. So in that case, that's where I would probably use stateless NAT, right? I mean, there is obviously a downside of stateless NAT that there is not much redundancy unless you configure it in a smarter way. But natively there is no redundancy with, you can't set up redundancy with stateless NAT, right? Yeah, so that's mainly when I would use stateless NAT, right? So that's when mainly I when I want to have like a one-to-one mapping, right? One-to-one mapping between what? Between my IPv6 hosts and the IPv4 addresses. When I want that one-to-one mapping, right? So when I want to map this guy with some address, right? That's when I would use, like, each of my IPv6 host, I want to map it with a unique IPv4 address. That's when I would go for stateless NAT. And in stateless NAT, there is also a nice feature where you can embed these addresses inside the IPv6 addresses, and I'll show you what I mean by that, right? But now that we're going to the stateless NAT, let's first look at the situation, right? Let's go to the distribution switch again. So this is the distribution switch, right? Let's look at the other VLAN, which we are going to look at for stateless NAT. What's the VLAN? VLAN 20. So let's go to VLAN 20. Show run interface VLAN 20, right? That's my VLAN 20. What do you observe here, right? So if you look at it here, what I've done is I have picked this one to be my /96 prefix for stateless NAT, which is 2001:166. And if you observe this, right, A02201, what is that? That's nothing but 10. If you convert this into IPv4, right, it's actually going to be what? Let me write it down here, 10.2.2.1. Right? So this is what I meant. You can embed IPv4 address inside IPv6 address. So this whole address is nothing but, actually, typically speaking, just take this, put it here at the start. There you go. This one, right? This is nothing but, when you put it in hex format, this is how you get it, right? And you see I've used /120. That basically means that what? this is nothing but mapping, or this address is nothing but mapping to /24. Right, there you go. So this is how the mapping really works, right? So the end hosts which are inside your IPv6 network, you normally configure them in a way that they embed the IPv4 address to which they are mapped to, right, inside the prefix. So now what really happens is that when you go to NAT64, we will explicitly tell NAT64, look, this is going to be your stateless prefix, right? And then it will strip this off. It will just look at this, right? And it will be able to make the forwarding decision based on that, right? There's a bit of routing which happens here and there, which again, you can figure it out by looking at the whole configuration, which I'll be sharing. But I just wanted to give you a glimpse of how the IPv4 embedded addresses, work in this whole stateless way, right? So let's come back to our NAT64, right? Now NAT64, okay, so we are here. What is the new configuration needed? Actually, it's pretty simple, guys. It's actually just a couple of lines of configs for enabling this, right? Obviously, the first thing, like I mentioned, you need to tell the NAT64 what is going to be your stateless prefix, right? In my case, it is going to be 2001:100:66/96. This is the prefix. So this is basically telling the NAT64, look, the traffic is going to come from this particular prefix, right? So anything coming from VLAN 20, you will have to jump on and do the translation for it, right? So there you go, that's gone. And the other thing is, obviously, once it strips off, once it gets traffic from this particular subnet, especially this particular subnet, once it strips this off, it will be left with what? It will be left with this network, correct? 10.2.20. What should it do with this? So we need to explicitly, right? We need to explicitly provide that information, and that also you provide it using another NAT64 command, which is, so it's kind of like routing is inbuilt into NAT64 when you talk about the stateless, right? So this is what you do. You say NAT64 route, and you're telling once you strip off, or once you translate from V6 to V4, once you get this 10.2.2, where do you have to send it, right? So so you will be sending it to the VDI 641, which is the V6 interface, right? So you can visualize this any way, right? I mean, if you want, I can actually again probably do a double click on my whiteboard. Give me one sec. Okay, so let me just give you a glimpse of that, because it's a pretty interesting topic, right? Just want to make sure it's very clear. Okay, so what we are trying to do with the stateless NAT, what we have done is we have picked the prefix 2001:100:66/96. Okay, that's the prefix. And what is the corresponding IPv4 subnet which we want to map to this prefix? That is basically 10.2.2.0/24. That is what we have done, right? So like I said, in stateless NAT64, this is what people mainly use it for, right? Where you embed this particular subnet, this 10.2, it's embedded inside this, the IPv6 network. So what really happens by doing this? Let's actually use a different pen, right? So now the traffic will be generated right from this particular end host, which is sitting here, or it can be generated by the IPv4 as well, right? The traffic can come from outside as well, or traffic can come from inside as well. We can actually let's trace it from outside to inside, right? Because we did inside to outside earlier. So let's trace it from here. What is the IP address on the top? It is 172. My pen is giving me trouble. Okay, 172.16. Okay, .1.1. Okay, pen is not doing well. Okay, so that's my put the 6 properly. Okay, so 172.16.1.1, right? That's my IPv4 host, which is on the outside. That wants to talk to what? It wants to talk to this particular host. What it will do, right? In fact, this particular host is, I don't know, think of it as 10.2.2.1 or 10 or something, right? So it will do a ping for 10.2.2.10. So it is going to do a ping because it's a v4, right? It can only talk to v4. So it will do a ping to 10.2.2.10. That traffic will be routed all the way to the NAT64, which is sitting here, right? The NAT64, which is sitting here, will see that the traffic is directed to 10.2.2 network. So it will get ready and start the translation, right? It will do the translation. So what it will do is it will obviously use the prefix, this /96 prefix, and it will attach that 10.2.2 at the end of it, right? It will create, it will create the new IPv6 address, and it will send the traffic all the way down, right, to my VLAN 20. Got it? So it's as simple as that, right? And obviously the source address, so it is obviously creating a new IPv6 packet here. The destination, we are all very sure, the destination is nothing but 2001:100:66, and then the hex value of 10.2.2.10. But the source will basically be again the same prefix, right? It will use the same prefix, but it will add this 172.16.1 at the end, right? So that will be the source. So that is going to be the packet which is going to come from here, the source and the destination. So that's the packet, and that packet will hit my client here, right? My client will obviously respond because it's a ping, it will respond, and that packet will be routed all the way back again to the NAT64, who will again reconvert it or convert it, strip it, move from v6 to v4, and it will send it all the way back here. right? That's how it works. Got it? Now, yeah, so that's literally how the stateless works. So let's actually configure it, right? So we have put these two lines. We gotta put the same thing on. I'm again not touching much on the routing side. You can figure the routing side by looking at the configs, because it would then probably make this video into a whole 2 or 3 hour session. I don't want to do that. So let's just stick to the NAT64 side of things. Okay, so that's good. I think that's it, guys. I mean, now I think we should be good to test this. Alright, so test it. So I'm going to go on my IPv4 only host, which is, let's go to the diagram. Right, so test it. I'll be going on my v4 host, and I will do a ping to this particular guy, right? But I'll be pinging its IPv4 corresponding IPv4 address, and we'll see how NAT64 will do the whole translation along the way, right? Just to make sure that I'm not cheating, what I'll do is let's go to the stateless host, right? Let's come here and let's probably enable debugs. Let's enable debug of ICMP, IPv6, ICMP, right? Just to show you that when I do a ping from the other side, you will see that the ping will actually appear here, right? And also, let me show you the address, showrun interface gig 1. So when you look at this showrun interface gig, sorry, I think it's 0/0. So when you look at the address, so what do I have on the stateless client? You can see the address is 2001:100:66. Look at this. What is this? This is nothing but, this is 10, this is 2, this is 2 and 10, right? So that's my IP address of this particular host. So technically I should be able to ping this guy from the IPv4 world. I should do a ping to 10.2.2.10, correct? So let's do that. Let's go to my IPv4 world, and I've also enabled debugs for you guys to have a look here. Right, I have enabled, yeah, debug is there. So I'll basically go and do a ping. There you go, right? The ping is going through, and there you go, the debugs are visible. So it clearly shows us that, and you can clearly observe the packet structure also, right? You can see here. So this is nothing but 2001:100:66 AC10. This is nothing but 172.16.1.1. So you see our NAT64 is actually doing all of this. It is creating this new packet. This is the destination, which is nothing but the stateless host, but you see this source is nothing but that. And then once it returns back, the NAT64 again converts it from v6 to v4, and that's how the ping is succeeding. Okay. Now typically stateless NAT, the whole idea is that you will obviously not get redundancy, right? But with some intelligent or smart way of designing it, you can actually do it. So what I have done is, I have using a bit of routing technique, right? And I will let you guys to explore that once you have a look at the configurations, which I'll put it on GitHub. But using a bit of routing, what I've done is I think stateless NAT also should work with like minimal downtime in case one of my device goes down, right? And I'll show you that. So I'm going to start a ping, right, from my IPv4 from outside to inside. The same thing will work from inside to outside, right? In fact, I can show it to you right now. Let's actually do that. So let's probably turn off the debugs. Let's pick this address. This is the address, right? Sorry, this one. This is the one we want to talk to. So that's the v4 host, right? This is the address. This is basically 172.16.1.1, right? So we're gonna do a ping. There you go. It works, right? So I just want to show you that both ways it works. Traffic can be originating from the v6 to the v4 world, or the vice versa. That being said, the other one which I also finally want to wind this conversation is with showing that you can do you can establish a bit of redundancy with stateless NAT as well. Let me do a repeat of, I don't know, maybe 1000. So the ping is starting, great. The ping is going through. What I will go and do is, let's do the same thing. Let's go and shut the link like we did earlier, right? Let's go to int gigabit 1. Let's do a shut. Okay. So now all of this goes down, but because what I've done is I've pointed my routing towards the redundant interfaces which I showed you earlier. So even if this goes down, the standby will pick it up, and the stateless NAT also will go through that, right? So there you go, right? You see there were few drops, but then it went through it, right? And I can actually bring it back again just by doing a no shut, right? I mean, this is good enough, right, for people. Like, I mean, this is stateless NAT, you're getting stateless NAT, but at the same time you're also able to do a bit of redundancy. But this is not possible out of the box. You can do it just by doing a bit of routing. You can point it to the redundant interfaces and that would take it. Okay, cool. So that's I did not expect this video to be this long, but I guess there was a lot of things to cover. But just to summarize, yeah, so that's what we did, guys. We actually, I'll paste these links, obviously, right? What we looked at was, we looked at these three topics mainly. We looked at stateful NAT, right? Actually, before that, we actually looked at the main problem, why we even go for NAT64, right? How NAT64 and DNS64 work together. Then we talked about how to configure stateful NAT64. We did stateful NAT64, and then we did interchasis redundancy, right? So that because they work together, they kind of are coupled together, right? They work together in tandem. And finally, we also looked at stateless NAT64, especially when you want to kind of embed your IPv4 addresses inside IPv6, right? And kind of instead of having to manually configure tens and hundreds of static mappings on the router, instead you can embed your IPv4 addresses inside IPv6 and then let the NAT64 strip it off and then kind of do the routing and use it in that way. And we were able to, how did we validate our solutions? We were able to talk from the stateful NAT64 to the IPv4 world outside, right? We were able to talk between V6 and V4. At the same time, we were also able to, we also did the other way around for stateless NAT as well, right? So for both stateful NAT64 and stateless NAT64, we were able to test that our solutions are working as expected. Alright, cool. Thanks a lot, guys, for watching. And yeah, you can try this on CSR1000Vs, ASR1 case, and even Cat 8 case, I believe, right? Alright, thanks for watching. And yeah, do let me know if there are any new topics you want me to cover. Just drop them in the comments. Alright, have a good one. Bye, guys.